Alright, so this will be a video for the first part of the Chapter 1 practice test. Basically, there's a 100% guarantee that the test that you get over Chapter 1 will be kind of a blend between the two practice tests that we have for Chapter 1. It's super rare that I ever put a problem on the test that isn't just like something on a practice test. So as you're studying for the Chapter 1 test, you should make sure you can do every single problem on the practice test absolutely perfectly, and that should help you go a long way in terms of doing well on the test. So I'll just jump into this. The first problem gives me a graph of a function that's f of x. And the first three questions are just kind of algebra questions. The first question asks me to find f of 0. And to find f of 0, I look across where I see 0 on the x-axis, and I look for any point. The y-coordinate of the point that is along that line is going to be the answer to that question. And there's kind of 2 points marked. There's the point 0, 0 that's marked with a closed circle, and there's the point 0, 1 that's marked with an open circle. Open circles aren't considered points on the graph, but closed circles are. The answer to problem 1a is going to be the y-coordinate of the solid circle, which is going to be 0. I'll do the same for part b. I'll look for 1 on the x-axis, and I'll look up and down that line that goes through 1 on the x-axis until I come to a point on the graph. And in this particular instance, there's only one point, and that point's the point 1, 2. The y-coordinate of that point is going to be the answer to this question. And lastly, f of negative 2. I see negative 2 on the x-axis. The only point that relates to negative 2 is this point negative 2, comma 1. The y-coordinate of that is going to be the answer. So the answer to that is going to be 1. Part D wants me to start tracing on the graph towards x equal to 0, but from the left side of it. So for part D, I'm going to start tracing on my graph, and I'm going to stop right before I get to that open circle, because that open circle has an x coordinate of 0, and the point that I'm pointing to is that same point 0, 1. The y-coordinate of that point, even though it's not a point on the graph, is the left-hand limit. To do the right-hand limit at 0, which is what part E wants, I trace along the graph going in this direction, and I point again, that points at the same point. The y-coordinate of that point is also the right-hand limit, which is 1 again. And then part F asks me for the limit as x goes to 0. It doesn't have a left-hand sign or a right-hand sign. It's a two-sided limit. If these numbers are different, the limit doesn't exist. If these numbers are the same, that's what the limit is. These numbers are the same, so this limit is equal to 1. Part G wants me to find the left-hand limit as I approach x equal to 2. Here's the x equal to 2 from the left side. So for part G, I'm going to trace along the graph and stop right before that point that has an x coordinate of 2. The y-coordinate of that point is going to be the limit, the left-hand limit, and that is the point 2, 1. The answer to part G, the left-hand limit, is going to be 1. Part H wants me to find the right-hand limit as I approach 2, so I'm going to trace along the graph, and I'm going to stop right before I get to the point that has an x coordinate of 2. And that's that point down there. The y-coordinate of that point, which I assume is negative 1, is going to be the answer to part H. The right-hand limit is negative 1. So left side, right side, two-sided limit is what part I wants me to do. If the left and the right-hand limit aren't the same number, when we're asked the limit when there isn't a plus or a minus sign, that's going to be does not exist. So absolutely no algebra, no calculus to do there. There's 9 different parts, and even if each one's 1 or 2 points on the test, that's going to be 9 or 18 points on the test if I do this many parts. Similarly, question 2 has a couple parts that don't require any symbolic manipulation. It's just understanding what the question is asking relative to the picture. 2 gives me the graph of a function f of x. It asks me to in part A to find the limit as x goes to positive infinity. Positive infinity is somewhere out here on the x-axis. And if I continue this graph, I'm assuming that this graph will get microscopically close to this dashed line, but never touch nor cross this dashed line. So the limit is going to be the y-coordinate of this dashed line. This is what the graph gets closer and closer to as the graph goes further to the right. When we're going to say the limit as x goes to positive infinity, I'm going to say is positive 2. For part B, I want the limit as x approaches negative infinity. Negative infinity is on the far left edge of the x-axis, and if I do the same sort of thing and continue this graph, the left-hand side, as the graph gets further and further, closer and closer to x equal negative infinity, the y-coordinate of the graph gets closer and closer to the y-coordinate of this dashed line, which is 2. So both of those are going to be 2. For question 3, it gives me a graph that doesn't flatten out, and it asks me the same sort of questions. The limit as x goes to positive and negative infinity. Positive infinity is way out to the far right of the x-axis, and I'm going to assume that this graph keeps going up and up and up and doesn't stabilize. When that happens, it's proper to say the limit doesn't exist. Some books might say that this limit is equal to positive infinity because it goes to the top of the y-axis, and the top of the y-axis has a y-coordinate of infinity. I always write doesn't exist, but I would completely live with infinity. And then for the left-hand limit, or the limit as x goes to negative infinity, this graph, as we go further and further down and to the left, it doesn't stabilize because it doesn't flatten out the graph. I'm going to say the limit doesn't exist. It would be completely okay if instead of saying doesn't exist, you notice that the graph eventually gets super low. It gets down to the bottom of the y-axis. If you said the limit as x approaches negative infinity was negative infinity because the graph gets to the bottom of the y-axis, that would be fine too. But I'll write D and E for the most part. Now we're getting in a bit of algebra, and the first problem, 4 is the first algebra problem, and it asks me to find a limit of a polynomial as x goes to 2. One strategy to find any limit is just to take the number that's given and plug it in for the letters. If you get something that's a defined number, that'll be what the limit is. So in part A of number 4, I just took the time to plug in 2 for each of the x's. I stopped writing the limit sign when I plugged in 2 for the x's. And if I simplify this, I'm going to get 9 for my answer. If I wanted to, I could have said the limit as x approaches 2 of x squared plus 4x minus 3 equals 9 for my answer, but that seems a bit overkill. So what I just circled in that box, the 9 should be the answer. In part B and part C, if you took the time to plug the number in like I did in part A, it's going to come out to a fraction that has 0 in the numerator and 0 in the denominator. And that will tell me that the limit likely exists, and there's algebra that I need to do to find that limit. Just to save some time, on the problem on the test where it gives you a fraction and asks you to find the limit, you're going to have to factor and cancel to actually get what that limit is. So I'm just going to skip the plugging the number in because I know that that's not going to get me the final answer to part B. So I'm going to factor the numerator. The numerator, the first have to be a couple of x's to multiply out to be x squared. The signs have to be a couple of pluses. My lasts need to multiply to 6 and add to 5, and that's going to be 2 and 3 because 2 times 3 is 6 and 2 plus 3 is 5. I'll factor the denominator. The first are going to be a couple of x's to multiply out to be that x squared. There's no minuses anywhere, so my signs have to be a couple of pluses. And the numbers after those plus signs have to multiply to 12 and add to 8, and that will be 2 and 6 because 2 times 6 is 12, and 2 plus 6 is 8. Now I'm going to cancel the x plus 2's, and now I can rewrite the problem as the limit as x approaches negative 2 of the fraction x plus 3 over x plus 6. Now I'm at a place where I can plug that number -2 in and not get 0 over 0 and actually get the answer to my question. So in the numerator for the x and in the denominator for the x, I plugged in -2. The numerator, I get -2 plus 3, which is positive 1. The denominator, I get -2 plus 6, which is positive 4. That's going to be the answer to part B. And I'm not going to write the whole problem with the answer. I'm just going to say the answer to part B is just 1/4. C is another one where I could take the time to plug in the number. I could, but I shouldn't. Say that the limit as x approaches 49 of this fraction is going to be the square root of 49 over 7 minus 49 over 49. You can, for any limit, you can take the value that's given, plug it in for the letter, and if you get something that's defined, then you're done. That's what the limit is. If you get 0 over 0, there's algebra that you can do to find out what the limit likely exists, but I have to do some algebra to see what it actually equals. In part B, I skipped the plugging in step because I just wanted to save time. And I probably should have skipped the plugging in step for this too. For this problem, we have to multiply by whichever the numerator or the denominator has the square root with the sign changed. So I'm going to multiply by the square root of x plus 7 over the square root of x plus 7. And the reason this is going to be a good thing is because when I simplify the numerator, it's going to make something cancel with the denominator. And the next step that I'm going to do to help me find the limit is I'm going to FOIL the top and I'm going to leave the denominator alone. So let me just do this foiling really quickly. The foiling I need to do is the square root of x minus 7 times the square root of x plus 7. And I'll do that by doing firsts, which are the square root of x times the square root of x. That's going to be the square root of x squared, and the square root of x squared is just x. I'm going to do outers, which is the square root of x times 7, and that's just plus 7 square root of x. I'm going to do the inners, which is minus 7 times the square root of x, which is just minus 7 square root of x. And I'm going to do the last, which is minus 7 times 7, which is minus 49. The outers and the inners cancel, and when I FOIL out that numerator, I get x minus 49. So all this work right here is just to help me do the foiling for the numerator. And now I'm going to rewrite the problem. I'm going to leave the denominator alone, but instead of writing the numerator like it was, I'm going to rewrite the numerator as x minus 49 because that's what you get when you FOIL the numerator. Good thing about this is I forced the x minus 49s to cancel. And when the x minus 49s cancel, I have to leave a 1 behind in the numerator because I can't write a fraction without a numerator. In the denominator, I've canceled the x minus 49, but I haven't done anything with the square root of x plus 7. I'm going to leave the square root of x plus 7 in the denominator, but I'm going to take it out of the parentheses because I no longer have factoring in the denominator. Now I'm going to plug in the 49 for the x and get 1 over the square root of 49 plus 7. That's going to be 1 over 7 plus 7. And my answer to part C of number 4 is the limit's going to be 1 over 14. For question 5, it's a limit at infinity of a fraction. And to do these kinds of limits using calculus and not using algebra shortcuts, I search the fraction and look for the highest power of x. In this case, it's x squared. And I rewrite the problem by multiplying every term by 1 over that highest power of x. I'm going to take the 8x squared, multiply it by 1 over x squared. I'm going to take the 1, multiply it by 1 over x squared for the numerator. In the denominator, I'm going to take the 2x squared, multiply it by 1 over x squared. and I'm going to take the 4x and multiply it by 1 over x squared. When I do that, a bunch of stuff is going to cancel and reduce. The x squareds in both the numerator and the denominator are going to cancel, and one of the x's between the 4x and the x squared is going to cancel. When I do this multiplying and after I simplify, I get the limit as x goes to infinity. This piece, there's no longer a fraction. It turns into 8 times 1, which is 8. This piece, it didn't reduce, and there should be a times here, not a plus. This piece, 1 times 1 over x squared is just 1 over x squared. This piece, the x squared, the fractions cancel. I'm left with 2 times 1, which is 2. This piece, the x stays in the denominator, and what's left here is 4 times 1, which is 4. So I've multiplied and have every x that's left in a denominator of a fraction, and that's kind of a good thing. Now I'm going to plug in infinity and stop writing the limit. So I'm going to say this is 8 plus 1 over infinity squared over 2 plus 4 over infinity. Any fraction with an integer in the numerator and infinity in the denominator is equal to 0. So I'm going to write this as 8 plus 0 over 2 plus 0. And that's going to be 8 over 2. And my whole answer to part A is going to be the number 4. I'm going to do the same thing for part B. And I didn't leave myself enough room, so I'll pull out an extra sheet of paper to do part B. For part B, the highest power of x that I see is x squared. And I'm going to multiply every single piece by 1 over x squared. So I'm going to multiply the 5x times 1 over x squared, the minus 4 in the numerator times 1 over x squared, and similarly, each of the 3 terms in the denominator, I'm going to multiply by 1 over x squared. And then I'm going to simplify all the fractions. The first fraction, 1x cancels from the 5x. It leaves me an x behind in the denominator because there were 2 x's. I only canceled one of them. This is going to turn into 5 times 1, which is 5 over x. I bring down the minus sign. Nothing cancels here. I'm just going to multiply the 4 times 1 and get 4 over x squared. Done with the numerator, I'll move on to the denominator. First piece in the denominator, the x squareds cancel. I'm left with 2 times 1, which is 2. Second piece, this x cancels with one of those 2 x's. That x turns into a 1. That x squared turns into an x. I'm left with minus 1 over x. And in the last piece, nothing cancels. I multiply the 2 and the 1 together and get plus 2 over x squared. Now I can plug in infinity for all of the x's. So I'm going to go, it's 5 over infinity minus 4 over infinity squared for the numerator, and then 2 minus 1 over infinity plus 2 over infinity squared for the denominator. All the fractions that have infinities in the denominator are equal to 0. So both fractions in the numerator are equal to 0, and the 2 fractions that are left in the denominator are equal to 0. So I can rewrite this as 0 minus 0 over 2 minus 0 plus 0. This simplifies to a fraction that has 0 in the numerator and 2 in the denominator, and any fraction with a 0 in the numerator is equal to 0. So the answer to part B is the limit's going to be 0. 2 more problems to do. One kind of tricky one where there's no algebra, so not a lot of partial credit. And another one that's a bit of algebra and not so hard to do. So 6 gives me a graph, and I'm supposed to find any points where the graph is discontinuous. Graphs are discontinuous where there's asymptotes, holes, or jumps. And for this graph, there's an asymptote at x equal to 0. So one of the values where the graph is discontinuous, I'm asked to find all the points where it's discontinuous, is at x equal to 0 because of an asymptote. The next point where it's discontinuous is at x equal to 2, because at x equal to 2, there's a hole. The third point where it's discontinuous is at x equal to 4, and I'll say that's because it's a jump. There's kind of a hole, but there's a jump between the graph that's not an asymptote. And the last place where it's not continuous is at x equal to 6. So there's 4 places where this graph either has an asymptote, a hole, or a jump, or maybe a combination. There's 4 values of x where it's not continuous. Now I need for each of those values to state a reason why it's not continuous. Let me try to see each one of these, if reason 1 fits. Reason 1 says the function isn't defined at the point of discontinuity. The function isn't defined at the point of discontinuity if I can draw a vertical line through that point and never get to a solid circle or a point on the graph. And at x equal to 0, the vertical line that I drew through the graph doesn't touch any open circle or any point on the graph. This means the function is not defined at that point of discontinuity, so reason 1 is a reason where it's not continuous there. If I do the same thing at 2, I go and I draw my line through 2, I never come across a point on the graph or a closed circle. So the graph isn't defined at x equal 2, so I'm going to put reason 1 there as well. If I do the same thing at 4, draw a vertical line, eventually I come to that point right there. That's a point on the graph. The function's defined at that point, so I can't do reason 1. Reason 1 only works if there's an asymptote and or a hole without a solid hole kind of matching up to it. Similarly, at x equal to 6, if I go up and down a line, I get to this solid circle, so the graph is defined there. I can't use reason 1 for that. I'm done with my reason 1s. I'm going to move on to my reason 2. So reason 1s, asymptotes, holes that don't have points underneath them or above them, that kind of plugs in the hole. The next thing is the limit doesn't exist. The limit doesn't exist if there's an asymptote or a jump. And at x equals 0, there's an asymptote, so the limit doesn't exist there. At x equal to 2, there's a hole, and the limit exists at a hole. At 4, there's a jump, and the limit doesn't exist at a jump, so I'm going to say that's reason 4. And at 6, there's a hole, but that's not a jump. The limit exists there. So the places where limits don't exist is going to be any place there's an asymptote, which is at x equal to 0, any place there's a jump, which is at x equal to 4. The last part of this says the limit doesn't equal the function value. This assumes that the limit exists. So for question 3, the limit has to exist. The limit doesn't exist at an asymptote. The limit doesn't exist at a jump. The only place where you might put the answer 3 is where there's a hole. And specifically, there'd have to be a hole and a solid circle. So for this, there'd have to be a hole along that vertical line with a solid circle that's somewhere else along that line to happen. And in problem 2, there's a hole, but there's no solid circle, so the function doesn't exist there. This doesn't work for asymptotes. It doesn't work for jumps. But for problem 6, or x equal to 6, there's a hole, and underneath the hole there's a solid circle. That's what reason 3 is. Reason 3 pictorially is a combination of having a hole capped with a solid circle under it. Reason 2 is having either an asymptote or a jump. Reason 1 is having an asymptote or an unplugged hole. So one more question, and I tried to make this question a little bit easier than on the video homework, and it's a big long paragraph, but it basically says look at each of the functions that are given and tell me if there's any points of discontinuity. And if there are points of discontinuity, just say what the points of discontinuity are, but don't give me the reason it's not continuous there. That's kind of what the first bit says. Find any values where the function is discontinuous. And then it goes on to say, but If there aren't any values where it's discontinuous, just say that it's continuous everywhere. So for this problem right here, part A is a fraction. I'm going to find the values of x that cause an asymptote. Graphs are discontinuous along asymptotes. And the algebra I'm going to do part A, I'm going to find the points of discontinuity by taking the denominator and setting it equal to 0. Each one of these computations for this problem are going to give me an asymptote, and functions aren't defined at asymptotes, and they're discontinuous there. So to do part A of number 7, to find the points of discontinuity if you're given a fraction, you simply take the denominator, set it equal to 0, you ignore the numerator, and you solve for x. So x equal to -5 and x equal to 1 are going to be the points of discontinuity for the graph in 7a. As a matter of fact, those are going to be the x coordinates of asymptotes. There's nothing more to do. I'm not asking for the reasons why it's discontinuous like I did on the graph. I thought this is enough here. Just being able to state the reasons from a graph I feel is enough, and this is a little overkill. Part B is a polynomial. Polynomials don't have any discontinuities or continuous everywhere. In my algebra, there's no algebra necessary to find the points of discontinuity here because there aren't anywhere. And in my instructions, it says if the graph is continuous everywhere, just say that it's continuous everywhere. And that's kind of what that says. So that's everything for the first part of the practice test. So get this perfected before you go on and try to get into the second half of the chapter.